In the last video, we covered this ideal AAS-based calibration curve analysis. Now, let's start talking about what can go wrong. The rest of this video will be dedicated to what I consider to be the most confusing of the three interferences we'll be covering, and that's called ionization interference. So here we go. We are now going to learn about the types of interference, starting with ionization. Sometimes those high-temperature collisions have so much energy that rather than excite the electron to a higher energy orbital, they completely eject the electron from the atom. In other words, it causes the atom to become an ion that's lost an electron. For many atoms, this is not a concern. At the temperatures of these experiments, collisions don't typically have the energy necessary to ionize an atom. However, for metals with low ionization energy, towards the left side of the periodic table, this can actually happen to an appreciable degree. So let's write metals with low ionization energy, metals with low ionization energy, which is a term you might remember from CHEM, although we're not going to get too into it. But the bottom line is, metals to the left of the periodic table will lose electrons at high temperatures. Lose electrons at high temperature, or temp. And the analyte in our example, which again is calcium, is no exception to this. There is some fraction of calcium atoms that can be ionized at these temperatures, which means that they will form calcium plus and they will lose the electron. Now, why is this a problem? Well, because an ion has different energy levels than its neutral atomic form, which in turn means that the delta E's between these levels is also different between the atom and the ion. So delta E of calcium is not equal to the delta E of calcium plus. Ask yourself why that would matter in a spectroscopy-based experiment. And you should have thought to yourself that the energy of light that's absorbed or emitted will be different. Light absorbed slash emitted is different. Which means we're not going to detect any calciums that are ionized because we're setting the detector to measure the absorption of the light that's absorbed by calcium, not calcium ion. So our signal will decrease. Signal decreases. So what's the fix for this? We can add an ionization suppressor, something that is more easily ionized so that it gives up electrons which the calcium in turn can take up. So let's write this. Ionization suppressor. Ionization suppressor. Add something more easily ionized. Add something more easily ionized. And if we were to go back into Gen Chem, we would learn the most easily ionized elements are from group 1. So group 1 typically. Add something more easily ionized so it gives up electrons which Ca plus takes up. So it gives up electrons which calcium plus takes up. In other words, we are suppressing the ionization of calcium by giving it electrons from something else. So this restores the calcium signal. Restores calcium signal. Maybe all the way up to 100%. Maybe up to 100%. So that it's not ionized at all. And so an example of an ionization suppressor would be potassium, which in that flame will definitely form some ions and produce electrons, which in turn can be taken by the calcium ion, so it reforms simple calcium, which is what we're trying to measure. The key is that if we had equal concentrations of calcium and potassium, potassium is just so much more easily ionized than calcium that it will produce far more electrons than calcium is going to lose. Beyond that, if we had higher concentrations of potassium compared to calcium, this effect will be further increased. Let's further emphasize this with a visual. So imagine that we have a sample that's just calcium represented by these white circles, and then a couple of them are just ionized by these high temperature collisions. So now we have these two calcium ions that will not be detected in our experiment. But now let's imagine that we had a different sample where those calciums were surrounded by electrons from potassiums that I'm not going to bother to picture. But I will show all of the electrons that have been produced. And so now we imagine the same type of collision happens. These calcium ions form, but they're surrounded by other electrons, which they're able to pick back up and reform calcium. And so now our sample has nothing but calcium atoms, and we can measure it properly. So hopefully that all makes sense. Again, I think this is the least intuitive of our three interferences. Let's actually see it in action in the context of our calcium experiment. Let's imagine that the standards we measured experienced some ionization, which is perfectly reasonable because those standards were simple. It was just calcium, nitrogen, and oxygen. Nitrogen and oxygen are not group 1 metals. They will not effectively be ionized. Thus, they cannot suppress the ionization of our calcium metal. On the other hand, the unknown was more complicated, and we were told that there were quote-unquote other chemicals in the solution. What if one of those chemicals was potassium, an ionization suppressor, and there was enough potassium to prevent any ionization of calcium in that unknown mixture? What would then happen to our calculation of the unknown's concentration? Well, this is where those three questions from earlier come into play. But the first thing I always like to do for this type of a problem is just draw a representation of the analysis going correctly. So this red line right here, this represents the calibration curve measuring true. In other words, all of our standards actually had a suppressor in them, and so ionization did not occur. And this represents our unknown measuring true and being plugged in and getting the correct concentration. So this is our reference point, and now we're going to see how we deviate from what should have happened. Now for the questions. Which sample experiences the interference? In this case, it's the standards that experience the ionization. 2. How does the interference change the measured signal? Well, we know ionization is going to cause the signal to go down. And that means that this calibration curve with no suppressor is going to measure falsely low. And then 3, what is the consequence on the calculated unknown concentration? Well, it is true that our unknown is going to measure correctly because again it has those suppressors in it. Unfortunately, that correct signal is being plugged into a falsely low curve. And so our analysis actually gives a falsely high reading. Right? This is rather counterintuitive. And if you're in 2124 and have done the AES experiment, you had to deal with this question, and you probably found it difficult. Students typically do. And so the answer to our question is we get a falsely high concentration calculation. Now be careful, because it's easy to start to think like, oh, when ionization effects occur, my answer is going to be falsely high. Well, that's only true in this particular scenario that I've outlined. But what if everything had the same amount of suppressors in it? Everything had the same concentration of calcium. Then what would happen? Well, we'd actually get the true reading. But what if I said that the standards had different concentrations of suppressors than the unknown itself, well, then we have no idea how the analysis is going to be affected, because maybe some solutions are more suppressed than others. As we wrote down earlier, we can't assume that just because a suppressor is in solution, all of the ionization will be prevented. This problem tells us that that's the case, but I might not always do that. And so again, don't memorize the scenario, memorize the 3 questions that you have to ask yourself, and you can take on anything I throw at you. So that's it for ionization interferences, and also an example of how we utilize those 3 questions. We'll cover the remaining interferences in other videos.